Okay, so welcome to this next video in which we are discussing the Western blot. Okay, so we're talking about adding our reducing agent to the loading volume. Okay, now we're assuming we're using dithiophenol rather than beta-mercaptoethanol. And basically dithiophenol usually comes in a concentration of 100 millimolar. Now you do not want 100 millimolar dithiophenol in your loading volume. What you would like is 10 millimolar. So you need to do a dilution of 10 basically. So if we therefore add in 2 microliters of dithiophenol, which is at 100 millimolar, then basically we will end up with a concentration of dithiophenol of 10 millimolar within our loading volume, because we have diluted it by a factor of 10. It's now in a volume 10 times bigger, but you've got the same number of molecules, and therefore its concentration has gone down by a factor of 10. Okay, so 5 microliters of these samples which you are loading into the wells of the gel will be loading buffer. 2 microliters will generally be dithiophenol of concentration 100 millimolar. The rest of it will either be your sample or water. And often you end up running many different concentrations of your sample, and I will explain why later once we've discussed the actual running. So basically what you might end up doing is you might end up making sample 1, so let's say sample 1 is going to be 5 microliters of loading buffer and 2 microliters of DTT. That's the same for all of the samples. And then the other 13 microliters that's available, remember we're trying to make a loading volume of 20 microliters. We've used up 7 microliters, so the other 13 microliters is still spare. We'll put in the cell lysate, okay, and we won't do anything to dilute that, okay, except of course adding it into the loading buffer and the DTT. Then we might do sample 2, so let's do sample 2 now, and we might say, okay, I want the concentration of protein now in sample 2 to be half. So if I now add half as much protein, then my concentration of the protein will be a half of what it originally was. Okay, so we would therefore add 6.5 microliters of cell lysate to sample 2, and of course that means we're adding half as much protein, so the concentration of protein in my final 20 microliters of sample 2 will be half of what it was in sample 1. Okay, then we can do sample 3, and let's say in sample 3 we want our protein concentration to be 1/5 of what it was in sample 1. So in sample 1 we added 13 microliters of the protein sample. If we divide that by 5, then we'll be adding 1/5 of the protein, and therefore in our final 20 microliters of loading volume we'll end up with 1/5 of the concentration of the protein. So if we divide this by 5, if we divide 10 by 5 we'll get 2 microliters. If we divide 3 by 5 we'll get 0.6 microliters. So this makes 2.6 microliters. Okay, so this is a 1 in 5 dilution compared to this one. And then finally, let's do now sample 4. Okay, so let's say we want a 1 in 10 dilution of the original sample 1, so we'll add 1/10 of the protein that we added in sample 1, so we'll add 1.3 microliters of cell lysate. Now in sample 1 what was brilliant is that we made up the rest of the volume of the sample. We took it up to 20 microliters just by adding the cell lysate, but in these other ones we're going to have volume left over. We will just make that up with water. So in sample 2 we'll obviously have to add then 6.5 microliters of water. Okay, in sample 3 how much will we have to add? Well, we're going to have to add 10.4 microliters to take up the entire volume of this, and this up to 20. Okay, so I'm just trying to make these two add up to 13 basically. And finally, for this one, I'm going to have to add in, what do I need to add to 1.3 to get 13? Okay, well it's going to be 11.7 microliters of water again. So I'll just put H2O. Okay, so those are our 4 samples. Now you might be wondering, well, why on earth are you bothering? It will become important later. You'll see why this is important. It's too difficult to explain at the moment, but we'll come on to it. Okay, so we now have our samples prepared. So in each of these we have differing concentrations of our cell lysate with the loading buffer, which contains either SDS or LDS and bromophenol blue. And we also have the reducing agent, which we've chosen as dithiophyretol. Okay, so now what we need to do is denature our proteins. We're going to do a denaturing gel electrophoresis. So we want basically to denature the proteins. Now what does that mean? Well, basically, proteins are usually in a complicated structure in three-dimensional space. So remember, proteins are polymers of amino acids, but they aren't just linear structures usually. They usually fold up into some elaborate structure, okay? So this is the 3D structure, or the folded structure of my protein. Basically, this is called the native form of the protein, okay? Now, the denatured form is the totally unfolded form, so when you just have a linear polypeptide, basically, like so. And in order to do that, we need to break all the bonds that are between the groups of the amino acids. So basically, why does it fold up like this? Well, it's because of interactions between the functional groups on the amino acids. Well, partly to do with that. And there's also, we can divide the interactions that take it into this 3D folded shape into two types. We can divide them into the secondary and the tertiary interactions. Now the secondary interactions are between the core amino acid structures, so the carbonyl groups and the amino groups of the peptide bonds. Okay, so those don't involve the R groups. The tertiary interactions involve the R groups. We want to break both of them. Now, most of these bonds can be broken just by heating the samples up, so that's what we'll then do. We'll take our 4 samples, which are in little test tubes. Okay, so here we have sample 1, for instance. We have another little tube which has sample 2 in. We have another little tube which has sample 3 in. And finally, a 4th little tube which has sample 4 in. And what we'll do is we'll heat all of them to 85 degrees Celsius. Now, 85 degrees Celsius will break most of the bonds, basically. It is not, however, enough to break the disulfide bonds. So if we had not added that reducing agent, i.e. dithiophyretol, then the disulfide bonds would not break. Even though most of the bonds would break at 85 degrees Celsius, the disulfide bonds between cysteine residues would remain intact, and that would stop the protein becoming truly denatured. So the reason we put that reducing agent in was to break the disulfide bonds so that truly it will linearize out, basically. So 85 degrees Celsius will break most of the interactions, and the dithiophyretol will do the last little bit, which is the disulfide bonds. Okay, so you might just ask, well, why can't we just heat it up higher? Surely if we heat it up high enough, the disulfide bonds will break. You see, the problem with doing that is that you'll start to get to temperatures where the peptide bonds start to break, i.e. the bonds between consecutive amino acids, and you don't want that. Okay, so you want to break the secondary and tertiary interactions without breaking the actual peptide links. So we don't want to heat it up too high. This is high enough to break most bonds, in fact nearly all of them except the disulfide bonds, and that's why we have the reducing agent. Okay, so we now have our denatured protein. So in each of these little test tubes, we now have our denatured protein. Now, of course, we're going to cool it back down. It's not going to remain at 85 degrees Celsius. So you should think instantly, well, surely when you cool it back down, the protein's going to fold up again, okay? And basically, that's what the SDS is for. So, we're now seeing the purpose of our reducing agent, and we're now seeing the purpose of the SDS or the LDS. We won't see the purpose of bromophenol blue for quite some time. Okay, so what is the purpose of the SDS? Well, basically, these dodecyl sulfate anions, they sort of end up surrounding the protein. They interact with the protein like so. So when the protein denatures and becomes linear like so, it ends up being surrounded by dodecyl sulfate anions. Okay, so once you dissolve sodium dodecyl sulfate or lithium dodecyl sulfate, what happens is the two ions, the cation, which is the sodium or the lithium, and the anion, which is the dodecyl sulfate anion, they separate from one another. Okay, and the dodecyl sulfate anions then surround the linear polypeptide like so. Okay, and they are going to stop it from ever being able to return to its native state. So even when you now cool it back down, it won't return to its native state because it's surrounded, basically. It can't. All of the groups are now surrounded by dodecyl sulfate anions and therefore can't physically interact with one another. Okay, so that's the purpose of the SDS or the LDS, to maintain the proteins in their denatured form. However, it does more than just that, because remember, all of these dodecyl sulfate anions, they have a negative charge, so they're all negatively charged. Okay, and we are now going to use this negative charge to separate the proteins out, to make them move when we put them within an electrical potential difference, basically. Okay, so they're going to move towards the positive, the area of a higher electrical potential because they are negatively charged. Okay, right. So, let's think about what has happened in each of these samples. So remember, all the difference between these samples is that we're calling this our base standard. So this is concentration 1. Of course, we don't know what its absolute concentration is. We just know what their relative concentrations are. So we'll set this as our standard, basically. So it's just number 1. Okay, this one is then a half. So the concentration of protein in this is a half of that one. This one's a fifth, and this one was a tenth. Okay, so think about what's happening in each of these. So the only difference is that they've got a different concentration, and we're not going to actually think about the reason we've done that for ages yet. Okay, so we can just think of them all as being equivalent because the same thing is happening in all of them. All of them had protein A, protein B, and protein C within. And now what will have happened is protein A, protein B, and protein C will no longer be in square, triangle, and circle shape anymore. They will all have been linearized. Now let's say protein A is the longest. So here it is. It's a nice long polypeptide. Let's say protein B is a very short one, and protein C can be somewhere in the middle. Okay, and of course they're completely now surrounded by SDS molecules. So all of the proteins in our samples are now linear polypeptides, and these polypeptides are surrounded by dodecyl sulfate anions. Okay, so what we're now going to do is we're going to load it into wells. We're then going to run the gel electrophoresis and separate out these proteins by size. Okay, so we now go to the gel electrophoresis. So this technique is known as SDS page. Okay, so it's a form of denaturing gel electrophoresis. As soon as you have anything to do with SDS, you know instantly that it was to do with denaturing. After all, what was the purpose of SDS? It was to keep the proteins denatured. So the instant you say SDS, we know that it's a denaturing form of gel electrophoresis. Okay? The page is short for polyacrylamide. Okay, so the A is for, the P is for poly, then the A is for acrylamide, and then the GE is for gel electrophoresis. Okay, so page for short. Now, basically, this is a technique to separate these polypeptides, these denatured polypeptides, according to their length. Okay, so polypeptides which are very, very short will be able to move extremely rapidly through the gel, whereas polypeptides that are very, very long, they won't be able to move so rapidly, they'll take much longer, so we can separate them out by size. Okay, but we'll explain this in more detail now. So basically, what you're going to create is a rectangle of gel. Okay, and usually what happens is this gel will come ready prepared. You'll just get it out of the fridge, basically. It'll be in a beautiful plastic container. You'll leave it in that container. You'll mount it into a special chamber, which I'm not going to even attempt to draw. I'm just going to highlight the theory of what we're doing here. Okay, so I'm not going to attempt to draw the chamber. If you've seen one, you've seen one. Okay, so basically you'll have this rectangle of gel. It'll be only a tiny sort of thick thickness, about maybe a few millimeters rather thick. Okay, but it will be a nice big rectangle of gel. Okay, and what you'll do is you'll mount it vertically. Okay, so at the top here, you'll then have the wells. Okay, and how many wells are we going to need? We're going to need four for our samples. Okay, but we're also going to need some for what are known as ladders, and we'll just have one ladder to make this simple. Okay, so we've got 5 wells here. So these are just where you load your samples. Okay, and this is basically a gel, and it's a polyacrylamide gel. So let me show you the structure of polyacrylamide. It's not a complicated structure. So it's a massive great polymer. Okay, so the gel consists of these massive great polymers. So let me show you. What you have is the repeating unit within the polymer is 2 carbons long, okay, like so. And then off the side here, you then have the amide portion, the primary amide. So you have a carboxylic acid group then linked to an amino group. This is your primary amide structure here. And basically this unit repeats again and again and again and again. So this is the structure basically of polyacrylamide. Okay, so it's a polymer of this repeating unit. And then right at the end, of course, you'll just have hydrogens coming off either end. Okay, so basically to explain this gel, you have got these huge great polymers running everywhere, forming a meshwork basically, like so. So in this gel you have a meshwork of these polymers, and this creates little pores through which things can move. So for instance, this here, which I'll highlight in turquoise, this is a little pore through which things can move. The idea of gel electrophoresis is that you are going to make your proteins, your denatured proteins, the long great polypeptides, you're going to make them fall through the gel. Well, I shouldn't say fall. They will, of course, fall. They will feel the gravitational force, but that's not the real reason they're going to move. That's not strong enough to actually make them move. It's something that we want to be on our side. You certainly wouldn't want to put the gel upside down because you wouldn't want the proteins having to fight gravity to move up. But the real reason they're going to move down is we're about to make this side positive and this side negative, so that they are moving this way because they are negatively charged effectively. We're going to apply an electrical potential difference of 150 volts across the sides of this gel. Okay, so that's what's going to make them move. But you certainly wouldn't want to put it the other way around because you wouldn't want them fighting gravity. Okay, and the idea is that basically the smaller ones will be able to get through these pores much quicker. They'll be able to sliver their way through the pores of the polyacrylamide gel much quicker. So in a certain amount of time, they will get much further down the gel, and we're going to run it for an hour, basically. And they will get a certain distance down this gel. And the longer ones, in that same amount of time, in that hour, they will have a much more difficult time slithering through the pores of the polyacrylamide gel, so they'll get much less far. Okay, so we separate out the proteins according to their length. Small proteins get much further, long proteins don't get as far at all. Okay, right, so this is the meshwork of polyacrylamide molecules. Okay, so what we're now going to do is load our samples into these wells, but actually I should just discuss one more thing before we discuss that. I just want to discuss what a running buffer is. Okay, so I'm going to discuss with you the concept of a running buffer. So basically, the entire gel here, this polyacrylamide gel, okay, it will be bathed in a solution, so it will be in a great big sort of tank, basically. So I'll try and draw this the best I can. So it will be mounted in a tank, and these things are ready assembled. They're little plastic tubs, okay, and you know, it will have all of the electrical stuff set up as well, so all you'll have to do is plug in 2 wires, okay. But I won't show all of that, I'm just showing it is basically a little tub here, okay, and the gel will be in contact with a fluid, and basically the fluid that you put around the gel is what's known as a running buffer, okay. So let me just complete my tank now. Okay, so we're going to bathe it in what's called a running buffer. Okay, to keep it nice and moist and make sure that the proteins can move through. Because, if the gel dries out, you can't imagine the proteins moving through a really dry, crusty gel. Okay, so you need to bathe it in a running buffer. Now, this running buffer will depend on what type of gel you're using. So, although you always use a polyacrylamide gel, okay, the components of this gel are far more complicated than just polyacrylamide. You'll have other things in there as well. Okay, so depending on the other things that you have in there, that will determine your running buffer. Okay, so let's now talk about the electrophoresis then. Let's mount our samples. So what we'll do is we'll mount sample 1 into this well here, we'll mount sample 2 into this well here, 3, 4, in some nice logical order. And then this one will be for what's known as a protein ladder. Okay, so what is meant by a protein ladder? Well, basically this is to give you some idea of what this actually means. So remember, what's going to happen is that the proteins are going to move through the gel, okay, and shorter proteins are going to migrate the furthest, and the longest proteins are going to migrate less far. So wouldn't it be nice to know actually how long each of the proteins are? Well, if you know a protein's got to, let's say, down here, and you won't be able to actually see this until we later do the immunoblotting, but let's say our protein's got down to here, it would be quite nice to know how long that protein is, okay? And basically what a protein ladder consists of is it will be a solution. So let's say here we have a little pot, and it will contain a huge number of proteins, and they will be denatured just like our proteins, so they'll be linear polypeptides now surrounded by SDS molecules, and basically you will have proteins of a set length basically. So maybe you'll have a protein of 100 amino acids, okay, and that will get very far. Then you might have one of 500 amino acids, maybe one of 1,000 amino acids, maybe the next one will be 1,500 amino acids. So basically you will know exactly what the lengths of the polypeptides in here are. And basically you will also often, these protein ladders, the proteins will have dyes attached to them, visible dyes, so that you can actually see the molecules. Good protein ladders, some of them won't, but some of them will actually be visible to you. You'll be able to see them as they move down the gel. Okay, so some of these proteins will then be labeled with something that colors them basically, so that you can actually see them. Okay. And they'll have different colours basically, so you'll get like a little rainbow coming down here, okay? And that will give you some idea of what actually it means for a protein to have got a certain distance. So for instance, if you find a protein, let's say getting this far in well 1, then what you'll be able to do is you'll say, here's my protein ladder. It's between my first one and my second one within my protein ladder. So let's say these are the first 2 lines that I see on my protein ladder. Now I know my smallest protein in my protein ladder was 100 amino acids, so this one is the 100 amino acid one. And I know my second smallest protein was 500 amino acids, so I know that this is where a 500 amino acid protein got to. So therefore I can say that this protein is somewhere in between my 100 amino acid and 500 amino acids, so it's somewhere, it's of a length somewhere in between that range basically. Okay, right. We will continue this discussion in the next video.